that will be by Professor Jarzebowska, and the title is Model-Based Control of a Third-Order Nonholonomic System.
Mr. Chairman, ladies and gentlemen, it's my pleasure to be here and to present a piece of my research. And my thanks go to Professor Luonga and to Sarah, who encouraged me to submit the presentation. So it was worth of that effort. We'll be talking about control today, and we'll be talking about control of non-holonomic systems. So first, I will try to introduce you into the merit of the problem, give you the motivation and the main focus of this presentation, and then the theoretical framework and the example in the end. So what's the underlying motivation? I'm really happy that it's in the same line as we heard in the morning during the introduction. The motivations are threefold. First, other researchers who strive to develop control strategies for systems with constraints, for example, these on accelerations. And it's really a kind of challenging problem and a problem of practical interest, because acceleration may lead to fast wear of the manipulators, and once you control manipulators, so the control goes smooth, and your actuators can live longer once you can avoid rapid changes on accelerations, for example. Also, I'm really happy to say that I found quite a lot of citations of my work, and it's really good news for me. And also a good news is that I could discuss certain things with these authors, and they use constraint equations only to derive control strategies. And what they do is that they design control strategies in which control inputs have to be recovered by integration. And when you go to a control engineer and tell him or her that you have to integrate your control inputs, so they don't like it, yes? It's really a problem. And also, real motion and control actions take place at the dynamic level, where the inertia properties, friction, and external disturbances are really significant. So it would be nice to develop control strategies designed at the dynamic level, not only taking the constraints only. And also, there are works, really nice works. So what I'm saying, it's not a criticism, but this is like what I could found in the literature, that there are attempts to design controllers taking analytical dynamics methods only. And then again, controllers designed like that are quite hard to implement. Again, control forces are nonlinear functions of state variables, and they are not, say, affine in state variables. So really, they are hard to implement. So what I'm saying, my presentation, my research I present right now is a kind of, say, interaction and discussion with these really good works. So I think that the full power of analytical dynamics methods and nonlinear control theory may be developed where both, say, methods, both tools are viewed as an integrated tool. So that's my motto, and I want to present the power of this combined, say, integrated approach. So I'm going to present a modeling platform which serves motion analysis and planning for a fast generation of control models, and then a control strategy which is a fusion of control-oriented modeling and nonlinear control algorithms. When you want to implement this, you may take, for example, embedded controller systems. Yeah? So first, let me go through a couple of examples really fast, but the reason is I want to introduce you into the problem. So we have the constraints, for example, on wheeled vehicles. We assume that the wheels don't slip. We call them material constraints, given by the nature in the sense that this is the way we describe the interaction between the ground and the rigid wheel. So it's classical. You take Lagrange equations with the multipliers, then you decouple the multipliers, and you can use nonlinear control methods, and it works. It works really well. Now, also, when the wheels are not powered, like in this snake-like manipulator, then the system becomes underactuated. It means that there are less control inputs than degrees of freedom. You need dynamic models. You can do partial feedback linearization, and still you can stay within Lagrangian methods and then move to nonlinear control. It's still okay. The same is for biologically inspired models. Here, the wrist is not underactuated. So the sportsman, also the falling cat, I don't like the example, but it's the same case. They are underactuated. Next, space vehicles. They are, when they are free-floating, they are underactuated. The base is not underactuated. Then there are less controls than degrees of freedom, and also conservation law. In control theory, the angular momentum conservation is treated as a constraint. The structure is the same as for the wheel rolling without slipping, so it's called non-holonomic constraint for space vehicles. Now, let's get closer and closer of what I'm going to talk today. Non-material constraints. It means that a designer, a control engineer add this is what we want. I want the system to do so and so, yes? And this is one of the first examples I generated some time ago. I need not a trajectory, but a trajectory property like the curvature be some specified function, so you get third-order constraint. Once it's non-integrable, we call it non-holonomic. Now, also a nice example, very practical, and this is part of my different research, is a desired motion of a vehicle with a pre-specified change of velocity and acceleration. See, this is the lateral acceleration and steering velocity. Can you see that the curvature and its derivative is here? So they are definitely higher order non-holonomic constraints. And if you work on vehicle performance, ride quality properties, you have to handle these additional requirements. And let's now arrive to the example of our interest. The end effector, the simplest case ever, to degree of freedom manipulator, and we want the end effector to move some pre-specified motion. This is the first thing, because it has to work. So do the work first. And also, we want some pre-specified velocity or acceleration or jerk. We want to control this when performing that specified task. Here is the example of the constraint. Definitely, it's not the classical constraint. This is not the constraint you can treat using Lagrange equations. So I'm in this control business for a while. So what I suggested to take the general form, a unified constraint formulation. For example, P equal to 2 is for the acceleration, P equal to 3 is for jerk. And once you have this unified constraint formulation, you may go to the multipurpose modeling framework. So you take these equations. Let's assume that you can present them in the form linear with respect to the highest derivative of the coordinate. And this unified constraint representation can be transformed into the classical state-space control form. But please remember that then it's neither kinematic nor dynamic because of this P, which can be higher than 2. Yeah? And the framework, the generalized program motion equations. I skipped the derivation, but if you are interested in this, I can deliver the proof that these are really the equations for the system with the constraints like that. Please notice, you can of course transform it to the state space control form, but only formally, yes? So we want to use this. Now, how to, okay, and here is just the transformation to this state space control form. Now, what we want to do, we have these nice equations. We say that this is the reference motion, the motion I want. For example, I want to control acceleration, I want to control jerk, yeah? And the control objective is formulated like this. Given a reference motion, this is what I want, you know, from the system to do. And my reference motion is specified by the constraint dynamics. Now, design a feedback controller that can track the reference motion. Yeah? And I mentioned these publications at the beginning of my presentation just to give you the idea that there are different solutions, but I suggest something more unified, and their works, discussions with them, were the motivation for me to look at this, say, acceleration and jerk business closer. Here is the strategy, the reference model. It can be dynamic, kinematic. This is what you want. Yeah, of course, you have to verify whether it's available for your system. Here is your feedback loop. Here is your dynamic control model. The dynamic control model is just dynamics without the constraints or with the material constraints only. And a control law, and a control law. I don't design any new controller. I take advantage of the existing controllers, but the strategy is new here, yes? So the platform takes advantage of the reference model, of the dynamic control model, yes, and you apply a controller. It's any control algorithm dedicated to nonlinear systems. Yeah? Advantages. Yeah? Advantages are that the control inputs are fine. They don't have to be recovered by integration. Then you can track any motion you can and you want to design. Yes, and the control dynamics is equivalent to Lagrange equations. The reference is not. Yeah? The reference is not. And of course, you can develop your control in non-adaptive or adaptive versions. Yeah? Modularity. You can add new blocks. You can add a velocity observer. You can add filters. Yeah? So it's really the advantage. So let's see how it works. So what's the assumptions, the requirements? The manipulator and effector is to track a trajectory with some specified curvature changes. Yeah, I did it purposely to have, say, third-order constraints, and also I selected first constant velocity. So do their work and keep constant velocity. So I combined this. This is for the trajectory curvature. This is for velocity. And in this case, the kinematic reference model. So here there are some details and numerical stabilization. Unfortunately, you have to add it when integrating these equations. And for, say, constant curvature, this is the reference motion. Draw circles. Then velocity, we want the velocity to be constant, and the tracking error. So here you can see it was, I think, PD, so you can even see that this is a PD. Now, the second case is the same. Do the work and keep the acceleration to be constant or not. Yeah? So these are the third-order constraints. And again, I may use the PDs or other controllers to get the specified acceleration. This is the reference acceleration for the end effector. And this is the controlled motion. So I start from the acceleration, which is really very far from the desired one. So it looks like this, but it would be much better to start closer to the conditions I want to get. So concluding the work, a kind of a multi-purpose modeling framework for designing motions which you need is, I think, a good idea, and it's very flexible. It's flexible with the modeling parameters, and also you can apply the existing controllers. Yes. So for the future, I'd like to add flexibility, yes, because you have control, but right now I showed an ideal case. Bodies are rigid. But once you apply fast motions, joint flexibilities, then you may get additional vibrations and should compensate for them. Yeah, so this is the plan for the future. So I think that it should work, and I think that I'll be able to show this in the future, like controlling flexible system models motion when they perform desired motions. So that's for today. Thank you very much for your attention.
Thank you. Any question in the audience? I have a very short question.
Yep.
I have not seen the noise in the measurement. What is changing in your approach?
Yes, exactly. So you can add filters. You can add filters. Means usually the signals which you measure are quite noisy. So, for example, I would add, say, Kalman filters, or maybe more advanced filters. Yes, you're absolutely. Oh. So, yeah. So you're absolutely right.
Okay.
You shouldn't assume that the signals are perfect. They are not. Yes. So due to the modular structure, probably you could add, say, filters.
Any other question? Michael.